it's a bunch of theorems about circles. It's a lot to remember, but the good news is it all just kind of makes sense. You know, it looks like it should be a certain way, and it is that way. Okay, so let's start with our first theorem here, 10.6, congruent corresponding chords theorem. So let's just say we have a circle. Okay, and I come in here and draw a segment across, or a chord I should say. Let's say we draw a chord, and I want to make this chord go from edge to edge, and I'm going to make it be 6 centimeters long. So chord AB is 6 centimeters long, and you can see that it kind of has this arc associated with it as well, doesn't it? We don't know what fraction of the circle that arc is, or how many degrees the arc is, anything like that. But here's the thing. If I come over somewhere else and I draw another segment that is 6 centimeters long, another chord that is also 6 centimeters, well, take a look. What do you think about arc AB and arc CD? Yeah, they're congruent. Okay, and not only are their measures congruent, but are equal, but they're actually congruent, aren't they? So we were talking yesterday about how two arcs can have the same measure but not be congruent, which is really weird. But these are actually, their measures would be the same. And then what if we kind of go in reverse, the converse I should say. Okay, so if we go in the converse of that, let's just say we have a chord here, and we know that the measure of AC is, let's say it's 45 degrees, and then I have another chord over here, DE, kind of naming them weird, but we know that the measure of arc DE is also 45 degrees. Well, what do you know about the two chords? Yeah, they have to be the same length, don't they? Okay, the only way they can cut an arc that has the same measure is if the two chords are the same length. So that's just the converse of the same theorem. Okay, seems reasonable. If you looked at it and had to guess, is that what you would guess? Yeah, and so it's something that's easy to remember. It's not a big deal. Okay. Next one down, perpendicular chord bisector theorem. Ugh. If a diameter of a circle is perpendicular to a chord, then the diameter bisects the chord and its arc. Did you get all that? I'm guessing you didn't. Should we go over it a little bit? Chloe?
Yeah.
Yeah? Okay. All right. So, here's what it's talking about. You know what I need? I need some paper with just a bunch of circles already drawn on it, don't I? Okay. So let's say we have a chord right here, and we have a diameter that is perpendicular to this chord. Okay. So a diameter's got to go through our center, doesn't it? Okay. So it's a special chord that goes through the center, and let's say that that diameter is perpendicular to our chord, like this. So this is a right angle right there. Okay? So if a diameter is perpendicular to a chord in a circle, then, well, what do you guys think? Look at this chord. Do you think that the diameter hits it just some random place along the chord? What does it look like? Yeah, it looks like it bisects it. It looks like it hits it at the midpoint, doesn't it? And that's in fact the case. It bisects that chord. Okay, this segment. And then what about this arc? Okay, if this is arc A, B, C, and the measure of arc AC is 90 degrees, well, what's the measure of arc BC? There you go. Yeah, 45. And it looks that way, and that's in fact the way it is. And also the measure of arc BA would also be 45 degrees. Was anybody thinking I was going to call this arc ABC when I named it? Were you kind of ready for me to do that, maybe? I'm not going to do that if the measure of the arc is less than 180 degrees, or even 180 degrees. It's a minor arc. It's less than a semicircle, isn't it? Okay. So I would never name an arc with 3 points unless I was going, around this direction. So if I want to talk about arc ADC, then I would name it that way. So this is a major arc, more than 180 degrees. What about arc DB? Oh, wait a minute. That's D over here. That's not there. Here. F. DF. It's on the diameter. BF. Can we get it right? Jeez, Mr. Collard. Here we go. BF. What's the deal with that? Semicircle. And does semicircle just mean some part of a circle? Like half, exactly. Okay, has to be exactly half. And when you talk about arc DF, does it matter if we go BF this way or BF this way? Does it really matter? It's the same thing, isn't it? Okay. All right. So we also have the perpendicular chord bisector converse again. So, all right. If a chord of a circle is perpendicular bisector of another chord, then the first chord is a diameter. If a chord of a circle is a perpendicular bisector of another chord, then it has to be a diameter. Now that's a little bit more. Okay? That's a little more than what the other one was talking about. So if I just have some random chord and I find its perpendicular bisector, which you guys know how to construct this. Oh, did I use the inside hole? Yes, okay. Got to make sure we do the same arc, don't we? If this chord is the perpendicular bisector of any other chord in the circle, then it is a diameter. That's kind of something, isn't it? Okay. So did you notice when I drew this circle, did I mark the center point of the circle? I didn't, did I? So if I'm trying to find the center of the circle, this is one way we can do it. I drew a chord, drew the perpendicular bisector. I know that's a diameter. I draw another chord, and I'm going to construct its perpendicular bisector. Try to keep everything a little bit different length so that we can. So now when I draw this perpendicular bisector, see how it's also a diameter? And what does that mean about where those two diameters meet? That's the center of the circle, isn't it? Okay. So if we just have a circle, and we need to know where that center is, can we find the center of the circle? Okay. So once again, some random chord, doesn't matter where it is, how long it is, anything like that. Construct the perpendicular bisector. Make sure you go more than halfway. So here is the perpendicular bisector. So that red one has to be a diameter, doesn't it?
Yeah.
And then we can do another. Got caught on there. That must be the center of our circle. We make it? It's right on the money, isn't it? Okay? So we located the center of the circle by drawing that. While we're doing construction, no, I'll talk about that when we talk about inscribed angles. Okay. So, look at the top of page 547. See a little example right there? One arc is labeled 11x. The other one is 70 plus x. And you're supposed to figure out what x is. So you need to know something about those arcs. You know, do they add up to 180? Do they add up to something else? Are they equal to each other? What's the deal with those two arcs? So does 11x equal 70 plus x?
Yeah.
Right, because notice the chord, HK, is bisected by that diameter, isn't it? Okay, and so that means that HN and KN, those two segments are congruent. They have the same length. Everyone see them? And it also means that the arcs have the same measure as well. So 11x does equal 70 plus x. You can solve that. All right, one more theorem. Turn the page over. Equidistant chords theorem. If two chords are equidistant from the center of the circle, then those two chords have the same measure. Don't you just love it when I read it and then you have no idea what I'm even talking about? All right, so look, here's what we're talking about. If I come from the center of the circle, if I come over here, I don't know, let's go 3 centimeters, and then I draw a segment over here that's perpendicular to that. Now that means that the distance from the center of the circle, center P, to chord AB is 3 centimeters. And remember, the distance has to be measured at a right angle. We can't measure from here to here and say that's the distance, can we? It has to be the shortest distance, okay? So now, if I have another chord that's the same length as AB, it's going to be the same distance away. So AB happens to be 6.9 centimeters. So if I come over here and draw one that is 6.9 centimeters, I'm kind of doing the converse here, but if this one's 6.9 centimeters and this one's 6.9 centimeters, then what would be the distance from point P to the chord CD? Yeah, it'll be 3 centimeters. So maybe I should flip it around so we have centimeters again. And move my book. I don't know if you guys could read it on my ruler, but if the two chords are equidistant from the center, then they're the same length. If they're the same length, then they're equidistant from the center. Okay? But again, does it look like it should be that way? That is the beauty of circles. Everything that looks like it should work, works. Okay? Anytime you look at something and think, well, it just seems like it should be that way. Yes, it is. And it's really easy that way to kind of figure things out. There are a lot of theorems to keep track of. I would suggest you have a picture of all 4 of these theorems in your notes, right? Picture, written out words, but then you draw the picture for it so that you have that for your test, and if you do that first before you do the homework assignment, it'll help out. Okay? So here's your homework for today. Should be kind of interesting. Chapter 10.3, 2, 6 through 10, the even, 11, 12 through 22, the even, and 26 through 28.